All right, today we're going to cover 9-4 and 9-5. We're going to start with 9-4, which is symmetry. Symmetry is a figure that can be folded and have the same image on either side of the fold. That's what we would call a line of symmetry, all right? So an example here, look at F. There's no line that I can draw through F that would cut it in half and it'd be the same on both sides. Now you look at this one, this is an isosceles triangle, and because it's isosceles, if we draw this line through here, we know everything on the left side of the image is the exact same as everything on the right side of the image, all right? And then a figure like this would have two, where you could draw one going left and right and one going up and down. Both of those would cut it in half. And then when you fold it over, it'd be the same. And then, of course, this one you have multiple lines of symmetry. They showed you 4 of them there, just like so. All right? So on these, how many lines of symmetry does each one have? Now, when you think about a butterfly, guys, a butterfly is the most common thing that people think about when they talk about lines of symmetry, because if you fold it in half, its wings will flap together and be the exact same. So it has exactly one line of symmetry, all right? Now, 2 here is a little bit tricky, but if I tell you that it is an equilateral triangle, that does change things. Once I tell you that it's equilateral, we know all sides are equal, then it would have 1, then it would have 2, and then it would have 3 lines of symmetry. All right. The next image we see, where you can draw one going left to right, and then you can connect all of these lines just like so. So there's 3 already. The ones that most people miss is you could actually extend lines out through here. So there's 4. Then you have 5, and a total of 6 lines of symmetry. Now, on a 4-leaf clover, you have one that you can go across here, one that can go across here, so that's 2. Then you put a 3rd and a 4th just like so. So it has 4 total lines of symmetry. All right. Point symmetry is a big one that they're starting to use a lot more. Point symmetry is a figure that can be rotated 180 degrees around the center point and be congruent to the original image. That's where, if you look at these, if I take this image right here and I rotate it 180 degrees, would it be the exact same? Yes, it would. You could do that with all of these, but it's a little bit easier if I can show you with a picture. So what I'm going to do now is I'm going to draw an S. This is the most common one that they like to test on. And then if I highlight that S, I can rotate it 180 degrees around, and it would still be an S. Now, granted, my S is a little bit crooked, but you get the idea of rotating it 180 degrees and it being the exact same. That's point symmetry, all right? So let's try a couple problems here. It says, this figure is apparently symmetric with respect to. If you see the image here, you have a heart, right? The line that cuts that in half would be the y-axis, right? So if we're asking what it's apparently symmetric to, it would be the y-axis only. All right? For this one, rectangle ABC is placed in a coordinate plane as shown. Which equation best describes the line of symmetry for rectangle ABCD? One thing you need for this problem is you need to remember, whenever you have y equals a number, what kind of line is that going to be? Well, that's going to be a horizontal line, which means it's going to go left to right. Whenever you have x equals a number, that means it's going to have an undefined slope, which means it would be a vertical line at whatever number it is. So let's go through and eliminate some of these options. The first one we look at says x equals 2. If I look at x equals 2, well, we know looking back up here that x equals 2 is going to be a vertical line where x is 2, which would be right here, correct? So is that a line of symmetry for the image? Clearly not, because it's shifted way too far to the right, correct? Let's try the next one here. This one is going to be y equals 5. Well, if we look at y equals a number, then it's going to be a horizontal line at 5. So we draw a horizontal line here at 5. Does that cut it in half? The answer would be yes. So that would be the one that it would be most likely symmetric to. All right? So make sure you do know your y equals a number and x equals a number graphs. That'll help you a lot on those. All right? 9-5, we're going to talk about dilations. A dilation is when each part of a figure is enlarged the same scale factor. For this one, the pre-image is the black square and the image is the blue square, which means we're starting with the black square. That's where we start at. And then our new image that we're creating is the blue one. You notice that this side length here is 3 and this side length is 9. So you should know that they multiplied the side by 3 to get it, so they have a scale factor of 3. All right? And you could do that just simply by saying, all right, well, we're going to take the 9 over 3. We reduce that and we would get 3, so the scale factor would be 3, which means they multiply each side by 3. All right? Sometimes when a dilation occurs on a coordinate plane, the figure will not only get larger, but it could also move. And here's how they're going to do that. In the example that they give us, they're going to tell us that our 4 points are these right here, all right, of the original pre-image. They want us to do a scale factor of 2 for our dilation, all right? In order to achieve it, we multiply the ordered pair by 2. So if we're looking at this first ordered pair here, we have 1, 2. Well, if I take 1 and multiply it by 2, that 1 then becomes 2. And if I take that 2 and multiply it by 2, then that becomes 4. So essentially, we're just multiplying every number in that ordered pair by 2. So let's try the next one here. We have 3 and 2, right? So we take the 3, multiply it by 2, it becomes a 6. Take the 2, multiply it by 2, it becomes a 4. So you'll notice if we graph both of those. Let's look at the first one again here. The first one was at 1, 2, which would be this point. And then when we moved it, it became 2, 4, which moved it up to here. So that's how it could move on that, all right? Same thing with all the rest. So hopefully you guys get the idea. You just multiply each number in the ordered pair by 2. So the 3, 4 then becomes 6, 8. And the 1, 4 then becomes 2, 8. All right? So at this point, we're going to go ahead and try these together here. It says find the scale factor of each dilation. So you guys got to remember, the blue one is the original pre-image, all right? The black one is going to be our new image. So we need to figure out how they went from the blue to the black, all right? So the way that you're going to do that is you're just going to pick any side and then its corresponding side in the other figure. For this one, let's use this top part. We see that that's 1 and 2 total spaces for the blue, right? Then we look at the corresponding piece. They go 1, 2, 3, 4, 5, and 6. So we would take 6, divide it by 2, and we would get a total of 3. So the scale factor would be 3 or 3 over 1, which means they multiply every side by 3. Do the same thing for our next one here. For this one, I'm going to pick the right side. It doesn't matter what side I use. That's just the one I want to choose. So we have 1, 2 in the original. So that goes on the bottom of the fraction. And then we have 1, 2, 3, 4, 5, 6 goes on top. 6 divided by 2 again would have a scale factor of 3. All right. For the third one here, guys, this is one that you've got to pay attention to, and the fact of 1, the original image is smaller or is larger. So instead of a scale factor of 3, it would probably be one that has a fraction like 1 over 3. But let's look to see what it is. So our original side. We're going to pick the top. We go 1, 2, 3, 4, and then we have 1, 2. So we would put the 2 over 4, all right? Because remember, the new image goes on top. We reduce that, and we would get a scale factor of 1/2. So instead of getting larger, it actually got smaller, all right? Same thing here. We got to figure out what our pieces are, right? So our original image, which is the blue, had a side length of 4 plus 2, which is actually 6. So that goes on bottom. The new one would be 4. If we reduce that, we would get a scale factor of 2 over 3. All right. For the next one, let's go ahead and do the blue first. 1, 2, 3, 4. That goes on bottom. And then we have 1, 2. That goes on top. We reduce that, we get 1/2. So it got smaller, and it got cut in half. All right. Same thing for the next one here. 1, 2, 3 goes on bottom. 1, 2 goes on top. Doesn't reduce, so that is our scale factor. So a scale factor for each dilation is shown. Make sure you understand that, and look forward to seeing you in the next class.